this lecture on machine learning and neural networks. Machine learning has revolutionized the way computers solve problems, marking a fundamental shift from traditional programming. In the past, every possible scenario had to be explicitly coded by developers. With machine learning, computers can now learn patterns directly from data, enabling them to adapt and improve over time without being programmed for every situation. This transformation is similar to teaching a person to recognize objects, not by listing every characteristic, but by showing them examples until they grasp the concept naturally. Understanding these foundational ideas is essential for any engineer or developer building intelligent technologies that drive innovation across industries today. Supervised learning is the most widely used approach in machine learning today. It involves training algorithms using labeled datasets, where each input is paired with the correct output. Imagine teaching a child to differentiate between cats and dogs. You show them many pictures, telling them which is which, until they can distinguish between the two on their own. The machine learning system works in exactly the same way, learning from these labeled examples and gradually improving its ability to make accurate predictions. To train and evaluate a model properly, datasets are divided into three subsets: training data to learn model parameters, validation data to tune hyperparameters and prevent overfitting, and test data to evaluate final performance on unseen examples. This is similar to preparing for an exam by studying, taking practice tests, and then sitting the actual exam. The two most common tasks in supervised learning are regression and classification. Regression involves predicting continuous values. For example, estimating house prices based on features such as size and location. If you have data on houses with varying sizes and locations along with their selling prices, a regression model can learn the relationship between these features and price, enabling you to predict the value of a new property. Classification, on the other hand, involves predicting discrete categories. A classic example is identifying whether an email is spam or not. Using labeled examples of spam and non-spam emails, the model learns to classify new emails into these two categories. Both regression and classification are powerful tools that underpin countless real-world applications across finance, healthcare, and technology. A crucial component of supervised learning is the loss function, which measures the difference between the model's predicted values and the actual correct values. The loss function guides the optimization process, ensuring the model continuously improves. Gradient descent is the most widely used optimization method. It works by iteratively updating the model's parameters in the direction that reduces the loss, based on computed gradients. Imagine a hiker trying to reach the lowest point in a valley by carefully taking steps downhill. Gradient descent works in exactly this way, navigating the error landscape to find the optimal model parameters. By repeatedly moving in the direction of steepest descent, the model converges towards its best possible performance on the training data. A neural network consists of artificial neurons arranged in layers: an input layer, one or more hidden layers, and an output layer. This structure draws direct inspiration from the biological neural systems found in the human brain. Each connection between neurons has an associated weight, controlling the strength of information flow. During forward propagation, each neuron computes a weighted sum of its inputs, adds a bias term, and applies an activation function to introduce nonlinearity. Activation functions such as ReLU, or rectified linear unit, enable the network to model complex and nonlinear relationships, much like how neurons in the brain fire in response to specific stimuli. The output of one layer becomes the input to the next, allowing the network to learn increasingly abstract and hierarchical features from the data. Backpropagation is the standard training algorithm for neural networks. It efficiently computes gradients across all layers using the chain rule of calculus. These gradients tell us how much each weight in the network contributed to the overall error, allowing us to update parameters in a way that minimizes the total loss. Backpropagation can be likened to a teacher providing detailed feedback on a student's performance, highlighting specific areas for improvement and guiding them towards better understanding. In practice, training a neural network involves repeatedly performing forward propagation to compute predictions, calculating the loss, running backpropagation to compute gradients, and then applying gradient descent to update the weights. This cycle continues until the model reaches satisfactory performance. Deep learning refers to neural networks with many hidden layers, capable of learning complex hierarchical features directly from raw data. One of the most significant developments in deep learning is the convolutional neural network, or CNN. Designed specifically for image processing, CNNs apply filters that slide across images to detect local patterns such as edges and textures. Each convolutional layer learns multiple filters, each responding to different features within the image. Early layers detect simple patterns like edges, while deeper layers combine these into more abstract representations, such as recognizing a complete face. Pooling layers are another critical component, reducing the spatial dimensions of feature maps while retaining essential information. This process is analogous to summarizing a large document into key points. Compared to fully connected networks, CNNs use far fewer parameters and exploit the spatial structure inherent in images, making them highly effective for visual tasks. Residual networks, also known as ResNets, introduced a powerful innovation called skip connections. These connections allow gradients to flow more easily across many layers, enabling the successful training of very deep architectures without performance degradation. This directly addresses one of the most challenging problems in deep learning, the vanishing gradient problem. In very deep networks, gradients can become so small that they fail to effectively update the parameters in earlier layers, causing the network to stop learning. By allowing information to bypass certain layers through skip connections, residual networks maintain strong learning signals throughout the entire network, making it possible to train models that are hundreds of layers deep. This breakthrough unlocked a new era of high-performance deep learning models. The practical applications of neural networks are vast and transformative. Autonomous vehicles rely on neural networks to detect pedestrians, recognize lane markings, and make real-time navigation decisions. In healthcare, medical imaging systems use neural networks to identify tumors and assist in diagnosis, enhancing both accuracy and speed. Natural language processing is another major area, where neural networks power systems that translate text, answer questions, and generate human-like responses. However, the success of neural networks depends heavily on data quality. Limited data hinders generalization, while biased or noisy data leads to unreliable predictions. Overfitting is a common challenge, occurring when a model memorizes training data rather than learning general patterns. Techniques such as regularization, dropout, and early stopping help address this. Regularization penalizes model complexity, dropout randomly omits neurons during training to prevent co-adaptation, and early stopping monitors validation performance to prevent overtraining. Training modern deep networks requires significant computational resources, often relying on specialized hardware such as graphics processing units and tensor processing units. These devices accelerate training by performing massive parallel computations, making it feasible to train large-scale models on enormous datasets. Despite their power, neural networks are frequently criticized for their lack of interpretability. Deep models function as black boxes, making it difficult to explain specific predictions. This is particularly problematic in safety-critical domains such as healthcare and autonomous systems, where understanding the rationale behind decisions is essential. Efforts are underway to develop techniques that provide insights into how neural networks make decisions. As artificial intelligence becomes ever more integrated into society, responsible development demands equal attention to fairness, transparency, and ethical considerations alongside technical excellence. By mastering both theory and practice, we can harness neural networks to create intelligent systems that genuinely enhance our world.